Imagine this. You're floating out in the calm, serene vastness of space, surrounded by billions of stars. Suddenly, you feel a pull, something you can't quite explain, a force stronger than anything you've ever encountered. It's not pulling you like Earth's gravity, it's pulling the very fabric of space itself. Welcome to the realm of a black hole. Black holes are among the most mysterious and fascinating objects in the universe. They form when the core of a massive star collapses under its own gravity, creating a point so dense that nothing, not even light, can escape its grasp. This boundary, known as the event horizon, marks the edge of the black hole, and once something crosses it, it's lost to the universe forever. But don't be too quick to fear them, I'd say with a smile. Black holes aren't cosmic vacuum cleaners waiting to gobble up everything around them. In fact, they don't go around eating stars or planets unless something gets too close. For the most part, they're just out there, minding their own business. The existence of black holes was once just a theoretical concept born from Einstein's general theory of relativity. But today, we know they are real. In fact, we've even seen one. Well, sort of. In 2019, the Event Horizon Telescope gave us the first ever image of a black hole, a supermassive one at the heart of a galaxy far, far away. And let me tell you, it's not just a hole in space. It's a doorway to some of the strangest physics we've ever encountered. You're probably thinking, how can we see something that doesn't let light escape? Ah, that's where things get interesting. We don't see the black hole itself. We see the light from material swirling around it, heated up as it falls into the abyss. That glow gives us a shadow of the black hole, a cosmic fingerprint of one of the universe's greatest mysteries. The birth of a black hole, the star that couldn't hold on. Let me take you on a journey back to the life of a star, a massive one. Imagine a cosmic giant, shining brightly for millions of years, fueled by nuclear fusion deep within its core. It's a balancing act. Gravity tries to crush it, while the energy from fusion pushes outward, keeping the star stable. But like all things in the universe, this delicate dance can't last forever. Eventually, the star runs out of fuel. It's as if it's been holding up a heavy weight for eons, and suddenly, it can't do it anymore. The outward pressure from fusion weakens, and gravity, relentless and unstoppable, takes over. Now picture this. The core collapses, shrinking to a tiny, unbelievably dense point. This collapse triggers a spectacular explosion, a supernova, a cosmic fireworks display brighter than an entire galaxy. What's left behind, though, is far more intriguing: a black hole. But let me assure you, this isn't just any kind of collapse. The core compresses into something so small and so dense that its gravity warps the very fabric of space and time. What once was a massive star, millions of kilometers across, is now a singularity, an infinitely dense point in space. Around it forms the event horizon, the ultimate boundary beyond which nothing can return. This, my friends, is the birth of a black hole. A remnant of a star that once illuminated the universe, now a cosmic enigma. What happens at the event horizon? Let's talk about something truly extraordinary. The event horizon. This is the point where everything changes. Imagine standing at the edge of a cliff, but instead of looking down at rocks or water, you're staring into the unknown, where even light itself can't escape. The event horizon is like the ultimate no-turning back zone. It's not a physical surface you can touch. It's a boundary. If anything, whether it's a spaceship, a planet, or even a beam of light, crosses this line, it's lost forever. It's as if the universe says, that's enough. You're not coming back from here. But here's the real kicker. As you approach the event horizon, weird things start happening. Time itself begins to slow down. You see, near a black hole, gravity is so strong that it warps space-time. For an outside observer, it might look like you're frozen in time, hanging at the edge of the event horizon. But for you, time feels normal, at least until you cross the line. Once you do, well, we can only speculate what happens next. The laws of physics, as we know them, no longer apply. Inside the event horizon, gravity is so intense that space and time are twisted beyond recognition. We call this the singularity, a point of infinite density, where even our best scientific theories struggle to explain what's going on. So, standing at the event horizon is like peering over the edge of the universe itself, into a place where time, space, and reality are fundamentally altered. It's a reminder that even with all our knowledge, the universe still holds mysteries we're only beginning to understand. The black hole's effect on space and time. Time dilation. Let's dive deeper into one of the most mind-bending effects of a black hole, how it plays with time itself. Imagine for a moment that you could hover near the edge of a black hole, right outside the event horizon. Time, as you know it, wouldn't tick the same way it does here on Earth. Near a black hole, time slows down, not just a little bit, dramatically. This effect is called time dilation, a phenomenon predicted by Einstein's theory of relativity. To an outside observer, you would appear to be moving slower and slower as you get closer to the black hole. In fact, if someone were watching you from a safe distance, they might never see you cross the event horizon. To them, you'd seem frozen in place, suspended in time. But for you, it's a different story. From your perspective, time feels normal. Seconds still tick by, and if you could somehow send a signal back to your friend, it would just seem like regular time to you. The closer you get to the black hole, though, the bigger the difference becomes between your time and the time outside. Now, here's where it gets even crazier. If you spend enough time near a black hole, just outside its event horizon, by the time you pull yourself back to safety, years, decades, or even centuries could have passed in the rest of the universe. It's like a one-way time machine into the future, but one you'd probably never want to use. This warping of time is one of the most fascinating aspects of black holes. It's a reminder that the universe doesn't always play by the rules we experience in our everyday lives. Near a black hole, the boundary between past, present, and future starts to blur. The biggest black holes in the universe, supermassive black holes. If you think the black holes we've talked about so far are impressive, wait until you hear about their bigger cousins, supermassive black holes. These aren't just stellar remnants. They're the giants lurking at the center of almost every galaxy in the universe, including our own Milky Way. These supermassive black holes are quite literally millions to billions of times the mass of our Sun. Let that sink in for a moment. Imagine something so massive that it warps not just the space around it, but entire regions of a galaxy. One of the most famous examples is Sagittarius A, the supermassive black hole right in the heart of the Milky Way. It's about 4 million times the mass of the Sun, and yet it's relatively quiet compared to some of its more active counterparts. In some galaxies, these titanic black holes are far more energetic. We call them quasars. A quasar is essentially a supermassive black hole that's actively feeding, pulling in huge amounts of gas, dust, and even stars. As this material falls in, It heats up to incredible temperatures and shoots out jets of energy so bright that they can outshine the entire galaxy they inhabit. These are some of the most powerful objects in the universe, visible from billions of light years away. But how did these black holes get so big? That's one of the great unanswered questions in astrophysics. Some scientists think they formed when galaxies first began to take shape, while others believe smaller black holes might have merged over time, growing larger and more powerful. What we do know is that these cosmic behemoths shape the galaxies around them. The gravitational pull of a supermassive black hole can influence the orbits of stars across vast distances. It's as if they're quietly orchestrating the motion of an entire galaxy, while we go about our lives on a tiny planet, completely unaware of the colossal forces at work. Black holes and the future of the universe. Now that we've explored the enormity of black holes, let's take a step back and think about their place in the grand cosmic picture. Black holes aren't just strange objects floating in space. They might actually hold some clues about the distant future of the universe itself. One of the most intriguing ideas is that black holes could be the last surviving objects in the universe. You see, everything in space, stars, planets, even galaxies, will eventually fade away. Stars will burn out, and over billions or trillions of years, what we know as the universe today will look very different. But black holes, they could stick around for an extraordinarily long time. There's even a theory, thanks to the groundbreaking work of Stephen Hawking, that black holes aren't completely eternal. According to Hawking, black holes can slowly lose energy through something called Hawking radiation. Over unimaginably long periods of time, this process could cause black holes to shrink and eventually disappear entirely. This isn't something that will happen tomorrow, or even in the lifetime of our sun, but in the distant future, it's possible that black holes could evaporate completely. But before that happens, black holes will continue to shape the universe. They might grow by merging with other black holes, becoming even more massive. Or they might quietly influence the galaxies around them, slowly consuming matter that comes too close. So, could black holes hold the key to the universe's fate? We're still trying to piece together that puzzle. What we do know is that these cosmic giants are far more than just powerful gravity wells. They're part of the larger story of how our universe evolves. We may never fully understand them, but that's part of the excitement. The deeper we look into space, the more we realize how much more there is to learn. As we've journeyed through the world of black holes, from their formation to the way they bend time and space, to the enormous supermassive black holes at the center of galaxies, it's clear that these objects are more than just the stuff of science fiction. They are windows into the most extreme parts of our universe, revealing laws of physics that challenge our understanding of reality. Even with everything we've learned, black holes are still shrouded in mystery. Every time we peer closer, new questions arise. What happens inside the event horizon? Could black holes be gateways to other parts of the universe or even other dimensions? And what will happen when the last black hole finally evaporates? These are questions that continue to inspire scientists and spark curiosity in all of us. The study of black holes isn't just about understanding some distant phenomenon. It's about uncovering the secrets of the universe itself. So, next time you look up at the stars, remember that somewhere out there, a black hole might be quietly spinning, holding within it the answers to some of the biggest questions we've ever asked. And perhaps, one day, we'll unlock those secrets. Until then, keep wondering, keep exploring, and keep looking up. nothing existed at the outset. After then, the cosmos began to take shape some 13.7 billion years ago. How this came to be, or if there was ever a time before, time is still a mystery. Yet, physicists have pieced together an approximate timeline of significant events in the cosmos's existence using telescope data and models of particle physics. From its beginning to its inevitable demise, we examine key points in the evolution of our universe here. Welcome to the endless universe. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. The Big Bang. The Big Bang is a moment in time, not a location in space, from whence all else unfolded. To be more precise, it's the first second of time, the point in history from which all other seconds have been measured. The Big Bang, despite its common name, was not an explosion, but rather a time when the universe was incredibly hot and dense before space began to expand outward in all directions simultaneously. The Big Bang scenario suggests that the universe was an infinitesimally small point of infinite density. However, this is merely a convenient way of expressing that we don't know for sure what happened at that time. We now understand the cosmos to break down at the Big Bang because mathematical infinities don't make sense in physics equations. Cosmic inflation era. The next cosmic confab was to rapidly expand in size. The universe may have expanded exponentially after the Big Bang, tearing off previously colliding parts of space. This period, known as inflation, is still mostly theoretical, but it has gained favor among cosmologists as a possible explanation for the striking similarity between distant parts of space. Attempts to detect this expansion in light from the early cosmos were reported in 2014. Nevertheless, further investigation revealed that the true culprit was nothing more than interplanetary dust causing interference. Quark-gluon plasma. The temperature of the early cosmos was between 7 trillion and 10 trillion degrees Fahrenheit, or 4 trillion and 6 trillion degrees Celsius, just a few milliseconds after the Big Bang. Quarks, elementary particles ordinarily contained within protons and neutrons, were free to move about at these temperatures. These quarks were combined with gluons, carriers of the basic force known as the strong force, in a primordial that pervaded the whole universe. In particle accelerators on Earth, scientists have replicated these circumstances. In both terrestrial atom smashers and the early cosmos, the challenging to achieve condition only lasted for a few fractions of a second. The early epoch. The subsequent period of time, beginning perhaps in the neighborhood of a few thousandths of a second following the Big Bang, was a period of intense activity. The universe chilled as it expanded, creating an environment conducive to the merger of quarks into protons and neutrons. The cosmic neutrino background, which has not yet been detected by scientists, was created 1 second after the Big Bang, when the density of the cosmos decreased sufficiently for neutrinos to sail across space without interacting with anything. The first atoms. Protons and neutrons fused together during the first 3 minutes of the universe's existence, creating the isotope of hydrogen known as deuterium, along with helium and a trace quantity of the next lightest element, lithium. Yet, this procedure ceased as the temperature dropped. As temperatures settled down 380,000 years after the Big Bang, hydrogen and helium atoms could join with free electrons to form the first neutral atoms. The cosmic microwave background, a remnant of this epoch first identified in 1965, was created when photons that had previously collided with electrons were able to flow without being disrupted. The Dark Ages. There was a lengthy period of time when nothing in the cosmos emitted any light. The cosmic dark ages refer to this time frame of around 100 million years. because practically all of what astronomers know about the cosmos can be gleaned by studying starlight. This era remains exceptionally challenging to study. It's hard to piece together what happened if there are no stars to guide us. The first stars. The first stars were formed when hydrogen and helium began to compress into massive spheres, some 180 million years after the Big Bang, creating hellish temperatures at their centers. After the neutral hydrogen atoms in interstellar space were broken apart into protons and electrons by the intense photons generated by early stars and galaxies, the cosmos entered a period known as cosmic dawn or reionization. It's hard to put a time limit on reionization. As it happened so soon after the Big Bang, its signals have been masked by subsequent gas and dust. Thus, the most that scientists can determine is that it was finished by around 500 million years after the Great Bang. Large-scale structure. Almost a billion years after the Big Bang, supermassive black holes developed at the cores of merging early galaxies. Intense quasars, visible from 12 billion light-years away, switched on and began emitting their bright beams of light. The universe's middle years. Throughout the subsequent few billion years, the cosmos underwent more evolution. Denser regions in the early cosmos drew more material due to gravity. A gorgeous filamentary cosmic web is the result of them slowly expanding into galaxy clusters and lengthy strands of gas and dust. Birth of the solar system. A yellow star with rings around it formed from a cloud of gas around 4.5 billion years ago in one galaxy. These accreted rings eventually became the 8 planets of our solar system, as well as numerous comets, asteroids, dwarf planets, and moons. Either the third planet out from the sun retained a lot of water via this process, or it received a deluge of ice and water from comets later on. Earth and humanity. Little primitive bacteria appeared on that third watery world between 3.8 and 3.5 billion years ago. These organisms arose and progressed into amazing marine monsters and enormous dinosaurs that fed on leaves. Some 200,000 years ago, upright beings emerged, capable of contemplating the vastness of space and learning about the universe's origins. The end, or not. It isn't the final chapter, of course. The future of the cosmos is still a mystery to physicists. It is dependent on our ability to accurately quantify the characteristics of dark energy, the unknown factor thought to be accelerating the expansion of the universe. All the stars and all the galaxies will have burned out, and even black holes will evaporate into nothing if the universe continues to expand forever, leaving behind a lifeless cosmos saturated with inert energy if this scenario comes to pass. Alternatively, the Great Crunch, a reversal of the Big Bang in which gravity triumphs over dark energy's expansionary force, will occur. The Great Rip, in which the cosmos rips itself apart, is another possibility if dark energy accelerates everything apart to greater and greater distances. Thanks for watching, and don't forget to hit the like button, subscribe, and turn on notifications for more content like this in the future. The universe is full of strange and surreal paradoxes that challenge our understanding of the world around us. From the mysteries of quantum mechanics to the mind-bending properties of black holes, the universe presents us with a plethora of phenomena that defy our intuition and challenge our perceptions of reality. This video lets you see some of the many things we do not understand in the universe and the strange and surreal paradoxes in what we think we understand. If you are interested in amazing videos about the universe, be sure to subscribe to our channel to stay updated. Everything we know represents just 5% of the universe. What is the rest? Normal matter, Protons, neutrons, and electrons make up just 5% of the universe. Staggeringly, the other 95% is something which we cannot fathom, see, or understand. We call it dark matter, which makes up 27% of the universe, and dark energy, which makes up 68%. But what are these mysterious components of our universe? Dark matter and dark energy are two mysterious concepts in astrophysics that scientists use to explain some of the strange observations that we make about the universe. Dark matter is a type of matter that does not interact with light or any other form of electromagnetic radiation. This means that we cannot directly detect it using telescopes or other instruments that rely on light. However, scientists can infer its existence by observing its gravitational effects on visible matter, such as stars and galaxies. Dark matter is thought to make up about 85% of the total matter in the universe, but we still do not know what it is made of. It does not behave like any of the known particles that make up ordinary matter, such as protons and electrons. Some theories propose that dark matter consists of undiscovered particles that do not interact with light or other forms of radiation, while others suggest that it may be made up of exotic objects such as black holes. Dark energy, on the other hand, is a hypothetical form of energy that is thought to permeate all of space and is responsible for the accelerating expansion of the universe. Unlike dark matter, which has a gravitational effect that slows down the expansion of the universe, dark energy has a repulsive effect that causes the expansion to speed up. The exact nature of dark energy is not well understood, but it is thought to be a property of space itself, rather than a type of matter or energy that we can directly observe. Scientists believe that dark energy makes up about 68% of the total energy in the universe. How many dimensions does the universe have? To the best of our knowledge, the universe as we know it has 3 spatial dimensions: length, width, and height, and 1 dimension of time, making a total of 4 dimensions in spacetime. This is known as the 4-dimensional spacetime. However, some theories in physics, such as string theory, propose that there may be more than 4 dimensions, possibly up to 11 dimensions. But these extra dimensions are thought to be curled up or compactified to be too small to be observed at our scale. This means that although they may exist, they are not directly observable, and their effects on the 4-dimensional spacetime can only be inferred through their influence on the physical phenomena that we can observe. These additional dimensions would help us unify the mathematical basis of the 4 fundamental forces of nature: the strong nuclear force, the weak nuclear force, the electromagnetic force, and gravity. Do these higher dimensions exist? And if they do, is there a way for us to measure their presence? Or will we forever be trapped in our 4-dimensional world? What if our universe is just one of a multitude out there? The idea that our universe is just one of many universes, known as the multiverse theory, is a popular concept in modern cosmology and physics. According to this theory, there may be many other universes existing alongside our own, each with its own unique properties and laws of physics. If this is the case, it would have profound implications for our understanding of the universe and our place in it. For example, it could help explain why our universe appears to be finely tuned to support life, known as the anthropic principle. If there are countless other universes with different physical laws and properties, it would increase the chances of at least one of them being able to support life. The multiverse theory also raises questions about the nature of reality and how we define what is real. If there are many different universes with different physical laws, are they all equally real? Or is our universe the only real one? What is time? Time is one of the most difficult properties of our universe to understand. Researchers say that time is a measurable period, a continuum that lacks spatial dimensions. There seems to be an obvious direction or flow of time, and it seems we can't travel backwards in time. Why is this? Are we trapped in the arrow of time, perpetually moving forwards? Is the passing of time intertwined with the way our universe works? According to the theory of Big Bang, time itself began together with the rest of the universe about 13.8 billion years ago. Does that mean that it makes no sense to ask what was there before? Time is a fundamental concept in physics and is often defined as the progression of events from the past, through the present, and into the future. It is a fundamental dimension in which events occur and is often represented as a continuous line or axis. In the context of physics, time is typically measured in units such as seconds, minutes, hours, and years. It is also an essential component of the space-time continuum, which is the four-dimensional fabric of the universe consisting of 3 spatial dimensions and 1 temporal dimension. The flow of time is often described as being unidirectional, meaning that it moves forward and cannot be reversed. This is known as the arrow of time and is often associated with the second law of thermodynamics, which states that entropy, the measure of disorder or randomness, in a closed system tends to increase over time. The nature of time is still a topic of ongoing research and debate in physics and philosophy. Some theories propose that time is an emergent property that arises from the complex interactions of the universe's fundamental components, while others suggest that time is a fundamental property of the universe, akin to space and matter. Particles violating the laws of nature? In certain situations, 2 particles can seemingly be in instant connection with each other, even if they are located at opposite ends of the universe. The phenomenon is known as quantum entanglement, where 2 particles can become correlated in such a way that the state of one particle is instantly correlated with the state of the other, regardless of the distance between them. While this may seem like a violation of the laws of nature, it is actually consistent with the principles of quantum mechanics. However, it is important to note that this does not allow for faster-than-light communication or the violation of causality. This is because, while the state of the entangled particles may be instantaneously correlated, there is no way to control or manipulate this correlation to transmit information faster than the speed of light. In fact, there is a fundamental principle in quantum mechanics known as the no communication theorem, which states that it is impossible to use entanglement to transmit information faster than the speed of light. So while quantum entanglement may seem like a strange and mysterious phenomenon, it does not allow for the violation of the laws of nature or the principles of causality. Could this feature of quantum mechanics one day allow us to send information instantaneously over large distances? Are we alone in the universe? There are at least 2 trillion galaxies in the observable universe, with more stars and planets in them than all the grains of sand on planet Earth. So, where is everyone? Why haven't we encountered life from elsewhere? Is life incredibly rare? Or does it have a limited lifetime, destroying itself before it has had the chance to seek out other life forms? What does this tell us about the future of humankind? The question of whether or not we are alone in the universe is one of the most intriguing and profound questions we can ask. Given the vast size and age of the universe, it seems unlikely that Earth is the only planet with the conditions necessary for life to emerge. There are likely billions of potentially habitable planets in our galaxy alone. However, the fact that we have not yet encountered any definitive evidence of extraterrestrial life is known as the Fermi paradox. There are many potential explanations for the Fermi paradox, including the possibility that life is indeed rare, that it is difficult for life to evolve beyond a certain point, or that intelligent civilizations have a limited lifespan and self-destruct before they can explore the galaxy. It is also possible that we simply have not looked in the right places yet, Our current methods of searching for extraterrestrial life are still relatively limited, and it is possible that more advanced techniques in the future could uncover evidence of life elsewhere in the universe. Does the self-reference problem distort our perception of the universe? We humans are also part of the universe we inhabit, so when we look out to study the stars and galaxies, are we really neutral observers of the universe? When we explore the universe, we are both observers and the subject of observation. How can we pretend to be neutral when we are deeply embedded in what we explore? Could it be that this self-reference problem affects the way we look at the universe and gives us an overwhelmingly wrong impression? The self-reference problem is indeed a complex issue when it comes to our study and perception of the universe. We are not neutral observers of the universe, but rather we are embedded within it. This self-reference problem can lead to potential distortions in our perception of the universe, as we may unwittingly project our own preconceptions and assumptions onto our observations. For example, we may tend to focus on phenomena that we find particularly interesting or relevant to our own existence, rather than taking a more objective and comprehensive approach. By acknowledging our own biases and limitations, we can work to develop more rigorous and objective methods of observation and analysis. Why is the universe seemingly so perfect for us? The universe seems to be perfectly made for us. But why is this? Why do the fundamental constants of our universe, such as the speed of light, have the values that they do, allowing life to exist? Could it be that there are infinite universes with infinite possibilities, and we merely happen to live in one that is perfect for life? There are a few possible explanations for this apparent fine-tuning of the universe. One possibility is the anthropic principle, which states that the universe is the way it is because it must be compatible with the existence of observers. In other words, the universe appears fine-tuned for us because if it were not, we would not be here to observe it. This is sometimes referred to as the selection effect. Why is it easier to destroy something than to put it back together? Entropy is the amount of disorder, chaos, or randomness in a system. One can never reduce entropy. Everything in the universe slowly moves towards disorder. It's very easy to smash a window, but impossible to put it back together exactly as it was before. The principle of entropy moves the universe from structure to chaos, from an ordered state to disorder. What does this tell us about the fate of the universe? As the universe continues to expand, it will eventually reach a state of maximum entropy, where all matter is uniformly distributed and there is no energy gradient available to drive further processes. This state is known as the heat death of the universe, where the universe will be cold, dark, and lifeless. The universe is not a closed system, as it receives energy from stars and other sources, but the overall trend is towards increasing disorder and chaos. However, it is important to note that this process will occur over an extremely long time scale, likely trillions of years in the future. Can anything escape a black hole? We have observed the effects of black holes, and we have seen one directly. The gravitational force of these massive objects pulls everything towards them, even light itself. What happens in the mysterious, infinitely dense center of a black hole? Could there exist such things as white holes, the opposites of black holes that spew matter and time into our universe? According to our current understanding of physics, nothing can escape a black hole once it has passed the event horizon, which is the point of no return. The gravitational pull of a black hole is so strong that it warps space and time, and anything that crosses the event horizon is inevitably pulled towards the singularity at the center of the black hole, where the laws of physics, as we know them, break down. We do not know what happens at the center of a black hole, as our current understanding of physics is unable to describe the conditions there. It is commonly believed that the matter at the singularity is infinitely dense and compressed to a point of zero volume, known as a singularity. As for the possibility of white holes, which are hypothetical objects that are the opposite of black holes, there is currently no direct evidence to suggest that they exist. White holes are hypothetical objects that are believed to exist at the other end of a hypothetical wormhole, which is a hypothetical tunnel-like connection between 2 points in spacetime. However, there is no direct evidence to suggest that wormholes exist either. The universe is full of strange and surreal paradoxes. Our quest for understanding these is only just beginning. As we continue to push the boundaries of our knowledge and explore the furthest reaches of space and time, we can be sure that the universe will continue to surprise and challenge us in new and unexpected ways, spurring us onto new and unexpected ways, spurring us onto new heights of discovery and understanding. Have you ever looked up at the night sky and wondered about the secrets it holds deep within its starlit expanse? What mysteries lie beyond the reaches of our sight, waiting to be discovered? Welcome to Unlocking the Universe, 10 mind-blowing cosmic mysteries. In today's journey, we're diving into some of the most astonishing and perplexing facts about the cosmos. From the mind-bending reality of black holes to the enigmatic forces of dark matter and dark energy, the universe is far more mysterious and incredible than we could have ever imagined. So buckle up as we explore these cosmic wonders and unravel the mysteries of the universe, one fact at a time. Fact 1. The size of the observable universe. Imagine trying to comprehend the full scope of where we are. It's a challenge that stretches the limits of our minds. The observable universe, the part of the cosmos we can theoretically see from Earth, spans about 93 billion light years in diameter. But what does that really mean? A light year is the distance light travels in 1 year, nearly 6 trillion miles. Now, multiply that by 93 billion, and you're just starting to scratch the surface of the sheer scale of our universe. Within this unimaginable expanse, there are at least 2 trillion galaxies, each brimming with millions to trillions of stars, and even more planets. Each light year, each galaxy represents a part of the universe full of mysteries yet to be explored. And as vast as the observable universe is, what lies beyond is even more intriguing. Because of the finite speed of light and the age of the universe, we can only see as far as light has had time to travel since the Big Bang. What exists beyond this cosmic horizon remains one of the greatest questions in astronomy. Fact 2. Black holes. These are some of the most mysterious and powerful entities in the universe. A black hole is a point in space where gravity pulls so much that even light cannot get out. The gravity is so strong because matter has been squeezed into a tiny space. Most black holes form from the remnants of a large star that dies in a supernova explosion. When the star's core collapses under the weight of its own gravity, it can compress to a point creating a black hole. In 2019, humanity got its first ever look at a black hole's event horizon thanks to the Event Horizon Telescope. This image captured a black hole at the center of the galaxy Mate 7, revealing the shadow of the black hole surrounded by a bright glowing ring of light, bending due to its immense gravity. The gravity of a black hole is so strong that it distorts space and time around it. If you were to approach a black hole, you would experience something known as spaghettification, where you'd be stretched into a thin strand of matter due to the gravitational forces. Our very own Milky Way galaxy harbors a supermassive black hole at its center, known as Sagittarius A. Supermassive black holes like this one might play a key role in how galaxies form and evolve over billions of years. Fact 3. Dark matter and dark energy. Though we can see stars, planets, galaxies, and even the light from distant cosmic events, these account for only about 5% of the universe. The rest is made up of dark matter and dark energy, which together compose about 95% of the total mass and energy of the cosmos. Dark matter, making up about 27% of the universe, does not emit, absorb, or reflect light. It neither glows nor can be directly observed. Yet we know it exists because of the gravitational effects it has on the visible matter around it. This mysterious substance binds galaxies together and is essential for the structure of the universe. The remaining 68% is dark energy, an even more mysterious force that is driving the accelerated expansion of the universe. Unlike anything else we know, dark energy appears to be a property of space itself. Since the Big Bang, the universe has been expanding, but thanks to dark energy, this expansion is not slowing down as previously thought. It's speeding up. This discovery in the late 1990s has transformed our understanding of the cosmos and its future. The enigmatic nature of dark energy poses one of the biggest questions in science. What is its true nature, and what does it mean for the fate of the universe? Will the universe continue to expand indefinitely, tear itself apart, or eventually stop expanding? Fact 4. The multiverse theory. While our universe is vast beyond comprehension, it might not be the only one. According to the multiverse theory, what we have traditionally called the universe could be just one of countless others in a grander multiverse. This theory extends from ideas in physics that suggest possible multiple universes may arise from the same quantum fluctuations that inflated our own universe. These universes might vary dramatically in their laws of physics, their configurations of matter, and even their fundamental constants. One intriguing version of the multiverse is the many worlds interpretation of quantum mechanics, where every decision creates a new split in reality, leading to new universes for each possibility. Imagine a universe where dinosaurs never went extinct, or where gravity is not a fundamental force. Theoretical frameworks like string theory and cosmic inflation provide some support for the multiverse concept, suggesting that the cosmos might consist of multiple dimensions beyond our familiar three-dimensional space. Each of these dimensions could potentially be a separate universe. The idea of a multiverse pushes the boundaries of our understanding and challenges the very notion of reality. It raises profound questions. If other universes exist, could we ever detect them? And what would this mean for our understanding of existence itself? Fact 5. Neutron stars. Among the universe's most extreme objects, neutron stars are the dense remnants of massive stars that exploded in supernovae. Despite their small size, typically about 20 kilometers in diameter, these stars pack a staggering amount of mass. Imagine the mass of the Sun over 1,000,000 times the mass of the Earth, compressed into a sphere just 12 miles across. The result is material so dense that a single teaspoon of neutron star matter would weigh about 6 billion tons. That's equivalent to the combined weight of all humans on Earth. Neutron stars are fascinating not only because of their density, but also their rapid rotation and strong magnetic fields. Some neutron stars spin hundreds of times per second. These stars can also appear as pulsars, which are neutron stars that emit beams of electromagnetic radiation. These beams are only visible when they sweep across the Earth, similar to the light from a lighthouse. Pulsars are so precise in their rotation that astronomers use them as cosmic clocks. Some neutron stars are known as magnetaires, which have the most powerful magnetic fields in the universe. These fields are so intense that they can cause starquakes and emit giant flares of energy, which can disrupt satellites and create spectacular light shows in the sky. Fact 6. The expanding universe. Since the dawn of the 20th century, astronomers have understood that the universe is expanding. This was first proposed by Belgian priest and astronomer Georges Lemaitre and later confirmed by Edwin Hubble, who observed that distant galaxies are moving away from us in every direction. What's fascinating is that it's not just the galaxies moving through space. The fabric of space itself is expanding. This means that with each passing second, every part of the universe is getting slightly further away from every other part. Scientists measure this expansion using something called redshift. As light from distant galaxies reaches us, it shifts to longer, redder wavelengths as space expands. This shift provides crucial information about the speed of the galaxy's recession due to the universe's expansion. These 6 cubes show the simulated distribution of galaxies at redshifts 9, 7, 5, 3, 2, and 1, with the corresponding cosmic ages shown. As the universe expands, the density of galaxies within each cube decreases from more than 500,000 at top left to about 80 at lower right. Each cube is about 100 million light-years across. Galaxies assembled along vast strands of gas separated by large voids, a foam-like structure echoed in the present-day universe on large cosmic scales. This visualization shows the number and clustering of simulated galaxies at different cosmic ages, ranging from 4% to 43% of the universe's current age of 13.8 billion years. Each cube represents a fixed volume of space, about 100 million light-years per side. Over the sequence, the expansion of the universe quickly lowers the density of galaxies. Each cube shows a specific cosmological redshift from 9 to 1, with earlier cubes cast in redder shades. Recent discoveries have revealed that the universe is not just expanding, but it's accelerating. This acceleration is thought to be driven by dark energy, an unknown form of energy that makes up about 68% of the universe. The implications of this expanding universe are profound. If the expansion continues indefinitely, the future of the cosmos could be a big freeze, where galaxies eventually drift so far apart that the stars burn out, leaving a cold, dark universe. Fact 7. The cosmic microwave background. Discovered quite by accident in 1964, the cosmic microwave background, or CMB, is a faint glow of light that fills the entire universe. It is the afterglow radiation left over from the Big Bang, and it provides us with a snapshot of the infant universe just 380,000 years after its inception. This cosmic relic was stumbled upon by Arno Penzias and Robert Wilson, who initially mistook it for noise from pigeons in their antenna. Their discovery provided strong evidence for the Big Bang theory, fundamentally altering our understanding of the universe's origins. The CMB is not perfectly uniform. It contains tiny temperature fluctuations that represent the seeds of all future structure, the galaxies, clusters, and vast voids that would eventually form. By studying these patterns, cosmologists can learn about the composition and evolution of the universe. At the time the CMB was emitted, the universe had cooled enough for electrons and protons to combine into neutral atoms, making the universe transparent to radiation for the first time. This moment is known as recombination. Today, advanced satellites and observatories continue to study the COM to glean more insights into the universe's rate of expansion, the nature of dark energy, and even hints about inflation. A theorized exponential expansion of the early universe that would have happened a fraction of a second after the Big Bang. Fact 8. Life's ingredients are cosmic. It's a humbling and fascinating fact that nearly all elements on Earth were formed in the heart of stars. This cosmic alchemy, where simple elements like hydrogen and helium are transformed into heavier elements, occurs under the extreme pressures and temperatures found in stars. Throughout their lifetimes, stars fuse hydrogen into helium, helium into carbon, and so on, up to iron. But the creation of elements heavier than iron requires even more dramatic events, such as supernovae and the collision of neutron stars. When a massive star explodes in a supernova, it releases an immense amount of energy and spews newly formed elements into space. Even gold, platinum, and uranium are forged in these cosmic catastrophes and the cataclysmic mergers of neutron stars. These elements, scattered across the cosmos, eventually coalesce into new star systems and planets, including our own. The carbon in our bodies, the oxygen we breathe, and the calcium in our bones all originated from stardust. So next time you look up at the night sky, remember that we are not just inhabitants of the universe, we are literally made of the universe. Every atom in your body was once part of a star far across the galaxy. We are, in the most literal sense, stardust. Fact 9. Exoplanets and the search for life. Since the confirmation of the first exoplanets in the 1990s, our understanding of the universe has expanded dramatically. To date, thousands of planets have been discovered orbiting stars outside our solar system. These exoplanets come in a fascinating array of sizes, compositions, and orbits. Among these, some are eerily similar to Earth, with conditions that may support life. Scientists use advanced telescopes like Kepler and TESS to detect these distant worlds by watching for the slight dimming of a star as a planet passes in front of it, a method known as the transit method. Particularly exciting are those exoplanets in the habitable zone, a region around a star where conditions might be right for liquid water, a crucial ingredient for life as we know it to exist on the surface. The quest to find extraterrestrial life is intensifying. Future missions plan to analyze the atmospheres of these exoplanets, searching for signs of life such as oxygen, ozone, and methane. Such discoveries could answer one of humanity's oldest questions. Are we alone in the universe? Every new exoplanet discovered broadens our perspective, reminding us of the vast possibilities that lie beyond our home planet. As we continue to explore, we not only learn more about the universe, but also about the potential for life's diversity beyond Earth. Fact 10. The youngest galaxies. By peering deep into the cosmos, astronomers are not just looking out in space, they are also looking back in time. Using powerful telescopes like the James Webb Space Telescope, scientists have been able to observe galaxies as they existed just a few 100 million years after the Big Bang. These observations are crucial because they show us the earliest stages of galaxy formation. The youngest galaxies are often small, irregular, and highly active, quite different from the large, well-structured spiral and elliptical galaxies we see in the nearby universe. Studying these young galaxies helps us understand how galaxies grow and evolve. For instance, we see that early galaxies were often much more chaotic, with high rates of star formation and frequent collisions that eventually led to the large, organized structures of stars we are familiar with today. These galactic youths are not just random patches of stars. They are the building blocks of today's universe. Observing them offers clues about the fundamental processes that have shaped everything we see around us, from the distribution of galaxies to the very structure of the cosmos. As technology advances, we will continue to push the boundaries of what we can observe. Each new discovery not only helps us piece together the cosmic puzzle, but also connects us more deeply with the origins of our own galaxy and ultimately our place in the universe. Thank you for joining me on this cosmic voyage. The universe is not just something out there. It's a part of us, and we continue to explore it. We learn more about ourselves. If you enjoyed this exploration, share your thoughts and questions in the comments below. What part of the universe fascinates you the most? Let's keep the conversation going. Don't forget to like, subscribe, and click the bell icon to receive updates on our latest videos. Together, let's continue to unlock the mysteries of the universe. NASA is one of the most prestigious and respected space agencies in the world, but it also has its fair share of secrets and mysteries. I wonder what NASA is trying to hide from us. The revelations below will surprise you. The enigma of the dark side of the moon. For decades, the moon has been a focal point of human curiosity and scientific exploration. As Earth's closest celestial body, it has been the subject of numerous missions, including the historic Apollo landings that captivated the world. Yet despite the significant efforts to explore and understand the moon, there remains one side that continues to fuel speculation and mystery. The far side, often referred to as the dark side of the moon. Unlike the side we are familiar with, the dark side of the moon is never visible from Earth. This phenomenon is due to the moon's synchronous rotation, meaning it rotates on its axis at the same rate that it orbits Earth, keeping one hemisphere perpetually hidden from our view. While unmanned spacecraft have captured images of this elusive region, the lack of direct human exploration has led to countless theories about what might lie beyond our sight. Some speculate that the dark side could harbor secrets far beyond our understanding. Could there be alien bases hidden away from the prying eyes of Earth, or perhaps remnants of an ancient unknown civilization? Others entertain the idea that NASA itself may be concealing knowledge of secret facilities located on the far side, operating outside public scrutiny. Why? After all, has there never been a manned mission to explore this uncharted territory? While NASA has conducted thorough scientific studies of the moon, these questions have yet to be fully addressed. Could the truth about the far side of the moon be more mundane? Or is there something far more fascinating that has been intentionally kept from us? Until a manned mission finally sets foot on the dark side, the mystery will persist, leaving the door open for even more speculation and wonder. The face on Mars? Coincidence or ancient civilization? Mars has always captured the imagination of humanity, often seen as the most likely candidate in our solar system to harbor life beyond Earth. Over the years, numerous missions have been sent to study the red planet, but one discovery from the 1970s has continued to provoke debate and inspire intrigue: the infamous face on Mars. In 1976, NASA's Viking 1 orbiter captured a series of photographs of the Cydonia region, revealing what appeared to be a massive structure with an uncanny resemblance to a human face. The image, with its distinct eyes, nose, and mouth, quickly became a sensation. Was this a remnant of an ancient civilization that once flourished on Mars? Or was it an optical illusion, a trick of light and shadow? For some, this face was undeniable proof of intelligent life on Mars. A message from a long-lost culture etched into the planet's surface, possibly to be discovered by future explorers. The excitement around the face on Mars wasn't confined to mere curiosity. It ignited discussions within scientific communities, conspiracy theorists, and the general public alike. Some saw this as the smoking gun, suggesting that Mars might have once been home to a thriving civilization capable of constructing massive monuments. Proponents of this theory drew parallels between the face and similar earthly formations, such as the Great Sphinx of Giza, which only fueled the argument that Mars, too, could have had its own builders. Despite the wave of enthusiasm, NASA responded cautiously, attributing the face-like formation to a simple, natural phenomenon. Subsequent missions, such as Mars Global Surveyor in 2001, captured higher-resolution images of the Cydonia region, revealing that the so-called face was, in fact, an ordinary mesa, a rocky outcrop shaped by natural processes over millions of years. Yet, for many, NASA's explanation did little to quell the mystery. Critics argue that NASA has been too quick to dismiss the face as a natural formation, and that the agency may have a vested interest in downplaying any evidence of extraterrestrial life. If the face truly was the result of an intelligent design, it raises profound questions. Who created it? What happened to them? And why did they leave this colossal image behind? While mainstream science leans towards natural geological explanations, the fascination with the face persists. It serves as a symbol of the larger question. Could Mars have once harbored life, intelligent or otherwise? And if so, how much of its history remains hidden beneath its rusty surface? UFO sightings. NASA's involvement in extraterrestrial encounters. Unidentified flying objects, UFOs, have fascinated and mystified people for decades. With each new sighting, the possibility of extraterrestrial life sparks a wave of speculation and intrigue. As one of the world's leading space agencies, NASA has found itself at the center of many of these discussions, both on Earth and in space. The agency's involvement in various UFO sightings and unexplained phenomena has left many wondering whether NASA knows more than it's willing to admit. Numerous incidents involving NASA spacecraft have been documented over the years, with some of them even captured on video and shared widely with the public. One such incident occurred during the STS-48 mission in 1991. Footage from this mission shows a small object in Earth's orbit making sudden, sharp movements, seemingly dodging what appears to be a missile-like object. To this day, the footage remains one of the most talked about UFO sightings involving NASA. While the agency offered explanations such as debris or ice crystals, the erratic movement of the object left many unconvinced, fueling theories that NASA may have encountered something beyond earthly technology. Another famous event occurred during the STS-75 mission in 1996, where a tethered satellite experiment resulted in a swarm of glowing objects surrounding the spacecraft. NASA described the phenomenon as debris illuminated by sunlight, but conspiracy theorists quickly latched onto the footage, claiming the objects were UFOs observing the mission. The unusual behavior of the objects, hovering, drifting, and seemingly interacting with the tether, led many to believe that these were not mere space particles, but evidence of advanced extraterrestrial craft. One of the more modern incidents took place during the STS-114 mission in 2005, when astronauts aboard the Space Shuttle Discovery reported seeing a strange object flying near the shuttle. NASA responded by saying that the object was most likely a piece of ice or insulation that had broken off, a common occurrence during shuttle missions. However, the sighting ignited a wave of speculation, with many questioning whether NASA was downplaying the significance of the event. The incident revived old suspicions that NASA may be involved in a cover-up concerning extraterrestrial encounters. While NASA consistently provides scientific explanations for these incidents, debris, ice crystals, or optical illusions, skepticism remains high among UFO enthusiasts. Some believe that NASA's role as a government agency compels it to suppress any information that might prove the existence of alien life. They argue that the agency's missions to the far reaches of space have likely uncovered evidence of extraterrestrial intelligence, but that such discoveries are kept hidden from the public to avoid panic or global unrest. Others point to the increasing number of declassified government documents related to UFO sightings as potential proof that NASA and other agencies have long been aware of extraterrestrial activity. Recent revelations by the U.S. government regarding unidentified aerial phenomena have only added to the intrigue. Could NASA's missions have revealed more than just distant planets and galaxies? Could there be an extraterrestrial presence that the agency is keeping from the world? Planet X, the elusive mystery of the solar system. For decades, the concept of a hidden planet lurking at the edge of our solar system has captured the imaginations of scientists and conspiracy theorists alike. Known as Planet X, or Nibiru, this hypothetical planet is said to exist beyond the orbit of Neptune, with a gravitational pull so strong that it could periodically swing close to Earth, causing catastrophic events. And whether NASA knows more than it lets on, The story of Planet X gained prominence in the 1970s when author Zecharia Sitchin claimed to have translated ancient Sumerian texts that described a mysterious planet called Nibiru. According to Sitchin, Nibiru was home to an advanced alien race known as the Anunnaki, who visited Earth in the distant past. These extraterrestrials were believed to have played a significant role in the creation of human civilization, shaping the course of history as we know it. The most startling part of this theory, however, is that Sitchin also predicted Nibiru's eventual return to Earth's vicinity, which he claimed would result in devastating global events. In the early 21st century, renewed interest in Planet X surged when astronomers observed strange gravitational anomalies in the outer solar system. These anomalies suggested that an undiscovered planet far beyond Neptune could be influencing the orbits of distant objects. Some astronomers began to seriously entertain the possibility of a large distant planet, although they didn't link it to Sitchin's theories of Nibiru and the Anunnaki. NASA, for its part, has consistently denied the existence of Planet X as described by conspiracy theories. The agency has pointed out that no credible evidence supports the notion of a planet periodically entering the inner solar system to wreak havoc on Earth. Additionally, predictions that Nibiru would collide with Earth or cause major disasters in 2012 were proven false, as the year came and went without incident. However, NASA's acknowledgement of the search for a Planet 9, a massive distant object that could explain the unusual orbits in the outer solar system, has kept the idea of a hidden world alive in some circles. For many conspiracy theorists, NASA's denial is simply another cover-up. They argue that the agency has long known about Planet X and its potential impact on Earth, but chooses to keep this information hidden to avoid causing public panic. Some even suggest that government elites have secret plans to escape to underground bunkers or off-world colonies when Nibiru inevitably returns to cause chaos on Earth. The Da Vinci Mission, unveiling the secrets of Venus. Among NASA's latest and most ambitious endeavors, the Da Vinci Mission, deep atmosphere Venus investigation of noble gases, chemistry, and imaging, stands out as a bold attempt to explore Venus, often referred to as Earth's sister planet. Despite Venus being closer to Earth than Mars, it remains one of the least understood planets in our solar system, mainly due to its harsh environment. With surface temperatures hot enough to melt lead, a crushing atmospheric pressure, and clouds of sulfuric acid, Venus presents an extreme challenge to space exploration. However, there are growing suspicions that Venus was not always the hellish world we see today. Some scientists believe that billions of years ago, Venus might have had Earth-like conditions, complete with liquid water oceans, and possibly even life. This raises the tantalizing question: what transformed Venus from a potentially habitable planet into the scorching inferno it is today? The Da Vinci mission, slated for launch in 2029, aims to answer some of these mysteries by sending a probe to dive into Venus's thick atmosphere. The mission will measure the chemical composition of the atmosphere, study its temperature and pressure at different altitudes, and provide unprecedented high-resolution images of the Venusian surface. With its advanced technology, Da Vinci could uncover vital clues about the planet's past, helping scientists understand why Earth and Venus, once so similar, evolved in such drastically different ways. Yet, as with many space missions, there are those who speculate that the Da Vinci mission might have objectives beyond what NASA has publicly disclosed. Could NASA be seeking evidence of ancient life forms or alien microbial colonies hidden in Venus's cloud layers? Some conspiracy theorists even suggest that Venus may still harbor life in its upper atmosphere, where conditions are much more temperate than on the planet's surface. NASA has consistently denied such claims, asserting that the mission's goals are purely scientific, aimed at studying Venus's atmospheric chemistry and history. Nevertheless, the idea that NASA could discover something far more profound during the Da Vinci mission has captured the imagination of the public. What if the probe uncovers signs of life or other extraordinary phenomena beneath the clouds of Venus? And if it does, what will NASA do with such groundbreaking information? The answers may not be known for years, But as the Da Vinci mission draws nearer, the anticipation grows. While many of these mysteries may eventually be solved through scientific inquiry, others will undoubtedly continue to provoke wonder and debate for generations to come. Whether NASA is hiding extraterrestrial knowledge or simply pushing the boundaries of space exploration, one thing is certain: our universe is vast, and we have only scratched the surface of what lies beyond. As we look toward the future, we can only imagine what other incredible discoveries await, and whether they will bring us closer to the answers we seek or raise even more questions. Have you ever wondered if somewhere in a vast and infinite cosmos, there's another version of you making different choices, living a different life? What if I told you that this might not just be a figment of science fiction, but a possibility grounded in the science of the very universe we inhabit? Welcome to a journey through one of the most mind-bending concepts in cosmic science: parallel universes. Today, we'll dive into the mysterious notion that our universe might just be one of many, an idea that challenges our very understanding of reality. The idea of parallel universes or multiverses isn't new. It has tantalized philosophers and scientists for decades, giving rise to numerous theories and debates in the realms of quantum mechanics and beyond. But what exactly are parallel universes? How did this theory come about? And why does it continue to capture the imaginations of so many? Today, we'll explore these questions and more as we delve into the science, the theories, and the profound implications of the possibility that our universe might be just one page in a vast library of realities. So let's step into the unknown as we ask the question: are we living in a parallel universe? Understanding parallel universes. As we venture into the concept of parallel universes, it's essential to begin with a foundational understanding. At its core, the idea of a parallel universe suggests that alongside our known universe, there exist countless other universes, each different from the last, potentially infinite in number. The roots of this concept are deeply embedded in the realm of quantum mechanics, a branch of physics that studies the smallest particles of the universe. Quantum mechanics tells us that particles exist in a state of probability until they are observed, leading to multiple potential outcomes. One of the most famous illustrations of this quantum uncertainty is the thought experiment known as Schrödinger's cat, where a cat in a sealed box is simultaneously alive and dead until someone looks inside. Extrapolating this to cosmic scales led to the idea that for every event that could happen, there exists a universe where it has happened. The theory of the multiverse posits that our universe, with all its vast complexity, is just one of an enormous number of universes, each following its own set of physical laws and constants. This multitude of universes forms what we call the multiverse. This theory was further popularized by Hugh Everett in the 1950s with his many worlds interpretations of quantum mechanics. Everett proposed that all possible outcomes of quantum measurements are physically realized in some world or universe. Imagine making a decision at a crossroads. In one universe, you turn left. In another, you turn right. Each choice leads to a new branching of the universe, creating a nearly infinite tapestry of possible outcomes. Understanding parallel universes requires us to stretch our imaginations beyond the conventional, to envision a reality far more complex and wondrous than we might ordinarily perceive. As we explore further, keep in mind the extraordinary implications of such a universe or universes, where anything imaginable might exist. Evidence and theories. While the concept of parallel universes might seem like pure science fiction to some, it is rooted in serious scientific theories and mathematical models. In this segment, we will explore the evidence and the key theories that support the existence of parallel universes. Though direct evidence of parallel universes remains elusive due to their nature, several scientific frameworks provide indirect support and have guided our understanding of these possible multiple realities. Quantum mechanics and the many worlds interpretation. The many worlds interpretation, first proposed by physicist Hugh Everett, suggests that all possible outcomes of quantum processes actually occur, each in its own distinct universe. This interpretation eliminates the need for wave function collapse, which traditionally resolves quantum uncertainty in a single observed outcome. Cosmic inflation theory. Cosmic inflation theory, a pivotal part of modern cosmology, proposes that the early universe underwent a period of exponential expansion. This theory suggests that such rapid expansion could lead to the creation of multiple disconnected regions of space-time, potentially each developing into separate universes with their own physical laws. String theory and the landscape multiverse. String theory, a candidate for the theory of everything, introduces the concept of the landscape, a vast number of possible false vacuums, each representing a different universe. According to this theory, our universe is just one of many bubbles in a larger multiverse, each with its own unique set of physical laws. The mathematical implications of string theory open up a multitude of possible universes, each solution to the equations potentially representing a different physical reality. Though these theories are compelling, they also present significant challenges, not least of which is their testability. The nature of these theories makes them difficult to prove or disprove, leading to ongoing debates in the scientific community about the validity and implications of positing such multiple universes. As we peel back the layers of cosmic science, the theories we uncover reveal a universe, or indeed a multiverse, far more complex and intertwined than we could have imagined. What might this mean for our understanding of our own universe and our place within it? Implications of parallel universes. As we delve deeper into the concept of parallel universes, it's crucial to consider the profound implications these theories hold for our understanding of reality, our place in the cosmos, and the future of scientific exploration. Philosophical implications. The idea of parallel universes challenges our very notion of existence and identity. If every possible outcome is realized in some universe, it raises significant questions about free will, destiny, and the nature of choice. In a multiverse, every decision you make spawns a new universe. This could suggest that free will is an illusion, as every possible decision and its opposite happens somewhere. Scientific and technological implications. Scientifically, the multiverse theory could revolutionize our approach to physics, potentially offering new ways to think about information, energy, and the fundamental structure of everything we know. It might even influence technologies we develop as we seek ways to detect or even communicate with other universes. Ethical and existential implications. The existence of parallel universes might also impose new ethical dilemmas. For instance, if there are infinite versions of us experiencing various degrees of suffering or happiness, how does this affect our understanding of morality? What responsibilities might we have to the well-being of our other selves, if any? Implications for cosmology and understanding the universe. For cosmologists, the multiverse theory could be key in solving persistent mysteries, like the fine-tuning of physical constants, dark matter, and the ultimate fate of the universe. It might help explain why our universe appears so precisely calibrated for the emergence and support of life. Understanding that our universe might be one of many changes the framework through which we view all cosmological phenomena. It adds a new layer to our quest to understand the origin and the future of not just our universe, but perhaps an entire spectrum of universes. The implications of parallel universes stretch our imaginations and challenge our deepest scientific and philosophical beliefs. As we continue to explore and debate these theories, we may find that the nature of reality is far more vast and varied than anything previously conceived. Pop culture and parallel universes. Parallel universes aren't just a topic for academic debate. They've also captured the imagination of artists, writers, and filmmakers, becoming a staple of popular culture. In this segment, we explore how the concept of parallel universes has influenced entertainment and why it resonates so strongly with audiences around the world. Parallel universes in film and television. From the Star Trek series to Stranger Things, parallel universes offer a narrative tool that allows for endless possibilities. These stories often explore themes of identity, destiny, and the human condition, posing questions such as, what if you could meet another version of yourself? What choices would you make differently? Parallel universes in literature. In literature, parallel universes have been a fascination long before modern physics provided a framework for them. Authors like Philip K. Dick in The Man in the High Castle and Neil Gaiman in Coraline have used parallel universes to examine alternate histories and realities, challenging readers to think about the what-ifs of history and personal choice. Video games and interactive media. Video games, too, leverage the concept of parallel universes to enhance interactive storytelling. Games like BioShock Infinite and The Elder Scrolls Skyrim allow players to explore different outcomes based on their decisions, providing a literal hands-on experience of a multiverse. As we've seen, from the quantum mechanics that suggest every possibility spawns its own universe, to the multiverse theories proposed by cosmology, and the philosophical questions about identity and choice, parallel universes compel us to rethink the very fabric of existence. As we stand on the precipice of new scientific discoveries, the theories of parallel universes remind us of the endless mysteries awaiting in the cosmos. Let us continue to question, to learn, and to explore the infinite possibilities that science and imagination can offer. If parallel universes exist, each choice leading to a new reality, consider this. What kind of world could your other self be living in right now? What dreams are they chasing? What fears are they facing? And most importantly, what can we learn from the idea that every possibility exists somewhere in the cosmic expanse of the multiverse? Thank you for joining us on this exploratory voyage into one of the most intriguing concepts of our time. Keep wondering, keep imagining, and who knows, maybe one day we'll find proof that we are indeed part of a vast multiverse. Imagine for a moment that 93 million miles away, a powerful force is brewing, a force so intense that it has the potential to disrupt your daily life in ways you wouldn't expect. I'm talking about our very own sun, currently experiencing one of the most turbulent and awe-inspiring phases of its life cycle, the solar maximum. Right now, the sun is buzzing with activity, and its effects are being felt across the universe and even here on Earth. Why should you care? You might wonder, what does this fiery giant have to do with me? Well, a lot more than you think. The sun's increased activity during this solar maximum doesn't just lead to beautiful auroras in the night sky. It can disrupt power grids, scramble your GPS, and interfere with radio communications. It's like an invisible storm raging across the cosmos, and it's influencing the technology we rely on every day. But to really grasp what's happening right now, we need to talk about the sun's 11-year cycle. Think of it as the sun's natural rhythm. It goes from quiet to chaotic and back again over a period of 11 years. At the start of the cycle, things are calm, fewer sunspots, fewer flares. But as we approach the solar maximum, all that changes. The sun becomes much more active, its surface crawling with sunspots, and bursts of energy explode in the form of solar flares. This is where we find ourselves now, right in the middle of this intense phase. Scientists from NASA and NOAA have confirmed that the sun is reaching its peak, and this solar maximum will continue for at least another year. So what does that mean for us? How does this massive ball of fire affect our modern world? And what can we expect as it continues to blaze with energy? Stay tuned as we dive into the fascinating world of the solar maximum, the science behind it, and why the sun is far more than just a bright light in the sky. Let's really dig into what's happening during this solar maximum. What exactly is a solar maximum? Think of it as the sun's stormy season, but instead of rain and wind, the sun's magnetic field goes wild. During this phase, the sun's magnetic field becomes twisted and tangled, leading to the appearance of sunspots, those dark patches you might have seen in solar images. But don't be fooled by their appearance. These sunspots are cooler areas, but they are where all the solar action begins. When the sun's magnetic field lines cross or tangle too much, they snap, releasing massive bursts of energy called solar flares. These flares are so powerful they can shoot out waves of radiation and particles toward Earth at incredible speeds. And when those waves hit us, they can have a very real impact. How do scientists know this is happening? NASA and NOAA are constantly monitoring the sun with specialized satellites and observatories, watching for these sunspots and solar flares. The latest data shows that we are smack in the middle of a solar maximum. Scientists measure the sun's activity by counting sunspots and tracking solar flare intensity, and right now, they're seeing an uptick in both. This heightened solar activity is all part of the sun's 11-year cycle, which shifts from quiet to chaotic. But don't worry, we're not talking about apocalyptic events. These are natural cycles that have been happening for millions of years, and they're crucial for understanding the sun's behavior and, by extension, the environment in space around Earth. What makes this solar maximum particularly interesting is that it's a little stronger than some scientists predicted. We're seeing more sunspots and stronger solar flares than expected, and that means the sun's magnetic field is even more twisted and dynamic than usual. But what does that mean for us? Let's talk about how this solar maximum affects you and me. When solar flares or coronal mass ejections, giant bubbles of solar plasma reach Earth, they can disturb our planet's magnetic field, creating geomagnetic storms. These storms can have a few different effects. In extreme cases, a powerful solar storm can overload power grids, leading to blackouts. Solar flares can mess with the electronics on satellites, causing communication and navigation issues. Think GPS not working or your phone signal suddenly dropping. On the bright side, these solar storms can also trigger stunning displays of auroras, those glowing, colorful lights in the sky, also known as the northern and southern lights. So while the solar maximum brings some risks, it also delivers one of nature's most beautiful shows. And who doesn't love the idea of gazing up at a brilliant aurora, knowing it's a direct result of our sun's activity? Now that we understand the solar maximum, let's zoom in on two key players in this cosmic drama: sunspots and solar flares. Sunspots are cooler areas on the sun's surface, but they're anything but calm. They're actually where all the action begins. Think of them as the sun's storm clouds. Sunspots form because the sun's magnetic field is all twisted up, and where these magnetic field lines get really tight and intense, sunspots appear. What's fascinating is that these sunspots can be enormous. Some of them are even larger than Earth. As they increase in number during a solar maximum, scientists keep a close eye on them because they tell us how turbulent the sun's magnetic activity is getting. Sunspots are also the birthplace of solar flares. Picture a rubber band stretched to its limit. Eventually, it snaps. That's what happens with the sun's magnetic field around sunspots. When the tension gets too high, the magnetic lines suddenly realign, and boom, a solar flare is born. Solar flares release enormous amounts of energy, equivalent to billions of nuclear bombs exploding at once. When a solar flare happens, it sends out intense bursts of radiation. Most of this radiation doesn't reach the surface of the Earth, but it can seriously disrupt our atmosphere. These flares can mess with satellite communications, knock out GPS systems, and even disrupt high-frequency radio signals. Imagine you're driving, relying on your GPS to navigate a busy city, and suddenly, no signal. That's a minor example of what a solar flare can do. For instance, in 1972, a solar flare knocked out long-distance telephone communication across several U.S. states. And while technology has advanced since then, we are even more dependent on satellites and electronics today, making us more vulnerable to these space weather events. Sometimes, along with solar flares, the sun also throws out huge clouds of plasma in what's known as a coronal mass ejection, or CME. These are the real heavy hitters of solar storms. If a CME is directed toward Earth, it can cause massive geomagnetic storms. When a CME reaches Earth, it can compress our planet's magnetic field and trigger geomagnetic storms. These storms can induce electric currents in power lines, potentially overloading transformers and causing widespread blackouts. One of the most famous examples is the 1989 Quebec blackout, where a geomagnetic storm caused a province-wide power outage. But CME don't just wreak havoc. They also create spectacular auroras. The particles from these solar storms interact with our atmosphere, lighting up the skies in vibrant greens, pinks, and purples. So while there's risk involved, there's also beauty in these cosmic phenomena. The more sunspots and solar flares we see, the more likely it is that one of these solar storms will hit Earth. That's why scientists are so interested in studying the solar maximum. They're not just observing for the sake of science. They're using this data to predict space weather and protect our technology. The better we understand these solar events, the better prepared we can be. Let's move beyond Earth for a moment and talk about space. During a solar maximum, the sun's increased activity doesn't just affect life down here. It poses a significant risk to astronauts and the technology we depend on in space. Imagine being an astronaut on the International Space Station, orbiting Earth as the sun throws out bursts of radiation. During a solar maximum, astronauts are at higher risk of exposure to dangerous levels of solar radiation. This can affect their health, causing radiation sickness and even increase the risk of long-term problems like cancer. That's why space agencies like NASA have strict protocols during heightened solar activity. If a strong solar storm is on the way, astronauts might have to take shelter in specific areas of the ISS that are better shielded from radiation. Then, we have satellites, those silent sentinels that orbit Earth, providing us with everything from GPS to satellite TV. During solar maximum, solar flares and coronal mass ejections can wreak havoc on these delicate instruments. You see, satellites are bombarded by charged particles from the sun, which can damage their electronics, causing them to malfunction or even fail altogether. One example of this happened in 1997, when a solar storm knocked out a major telecommunications satellite, causing issues with TV signals, credit card transactions, and even pagers back when we still used those. Today, we rely on satellites even more, and a similar event could have widespread consequences for communication and navigation systems. How do scientists protect against this? NASA, NOAA, and other space agencies monitor the sun's activity closely. tracking sunspots and solar flares in real time. They use this data to predict space weather and issue warnings when solar storms are coming. This allows engineers to put satellites in a kind of safe mode, where they limit non-essential functions to protect sensitive electronics from being fried by solar radiation. Engineers also build shields into satellites to protect them from these radiation blasts. It's like giving our tech in space a layer of cosmic armor. But even with these precautions, solar storms are unpredictable, and the most powerful ones can still cause damage. Let's bring it all together. We've seen how the sun, in its solar maximum, can cause a cosmic storm affecting life on Earth, and even beyond, from disrupting power grids to threatening astronauts. But it's not just about the risks. It's also about learning and preparing for the future. The solar maximum will continue for another year or so, giving us a unique opportunity to study the sun during one of its most dynamic phases. And as we prepare for future missions to the Moon, Mars, and beyond, learning about solar activity becomes even more crucial. The sun, once thought to be an unchanging ball of fire, is actually a living, breathing star with a profound impact on our lives. We're all connected to this massive star in ways both visible and invisible. Whether it's powering your GPS, dazzling you with northern lights, or sending a storm that shakes up space, the sun's cycles are a cosmic reminder of our place in the universe.